Yeah, hello. So this is the fourth tutorial session for the NPTEL course on variational calculus and its applications in control theory and nanomechanics. So I'm G.R. Krishnachan Avatar, doing my PhD in aerospace engineering at Indian Institute of Science, Bangalore. So as usual, I would be following the same pattern while during delivery of my tutorial session. So the overview will be that I will start with revisiting the concepts that we learned in the week 5 of this course, which is essentially on holonomic and non-holonomic constraints and also introduction to variable boundary points. Thereafter, I would be doing a set of solved examples for all these three types of constraints, followed by a few problems on various variable boundary points. So essentially, this is going to be we'll be just introducing those variable points in such a manner that the domain is fixed. However, the value of the dependent variable at the ends may or may not be variable, or either one or both of the boundary values may be variable. So let me just give a review with what we had discussed in the previous tutorial session. So essentially, it was we had introduced this constraint extremization. So as it's well known to all of us that when the resources are limited in nature, and this reduces the number of options that we have in order to carry a task. So in mathematically, we call such limitations, we model such limitations in terms of constraints. And this is via putting limitations, limitations in terms of both dependent and independent variables. And and in variational calculus, we often, there are three classes of constraints. And the first one is the integral constraints. So this constraint is of the form of, as I have shown here, it's defined over an integral g as a function of x, y, and y prime, and this happens to be a constraint. Problems with integral constraints are known as isoparametric constraints. Then we follow it up with algebraic constraints. So algebraic constraints are those constraints for which the expression happens to be g as a function of x, where x is the independent variable and just the dependent variable y. And this problems with such constraints are called as holonomic constraints or holonomic problems. Then the third type of constraint is differential constraints, in which the constraints are represented in a general form of g, x, y, and y prime. So one thing to notice here is, which differentiates differential constraints from algebraic constraint, is that even the derivatives of the dependent variables are also a part of the constraints. So problems with such form of constraints are called as non-holonomic problems. Let me start with the first constraint, or it's more of a review. So the first constraint is isoparametric problems. So it should be one here. So here we extremize the functional of the form of j y is equal to x naught to x1 f of x y y prime dx, whose extremals satisfy the boundary conditions y at x naught is equal to y naught, y of x1 is equal to y1, and an integral constraint which is defined as I of y is equal to integral over x naught to x1 gx y prime is equal to L, and this happens to be a constant. So the necessary condition for extremum is given by d by dx of partial derivative with respect to y prime minus partial derivative of y of the quantity f minus lambda j, where f happens to be the integrand of the functional j, and g is the integrand of the functional or of the integral constraint I. And lambda is a real number, and it's also known as Lagrange parameter, Lagrange multiplier. And the second type of constraint that we had just listed in a couple of slides ago is holonomic or algebraic constraints. So it tends to have, so given a functional j, which is defined over the domain x0 to x1, or in this case it will be it should be t0 to t1, over a t0 to t1 of the integrand happens to be L, which is a function of t, q vector, and q dot vector, where q vector is a column vector consisting of n dependent variables, which are q1, q2 to kn, subject to boundary conditions at the ends, or also known as endpoints. So q vector at t0 is equal to q0 vector, and q vector at t1 is equal to q1 vector. So the necessary condition for extremization are given by the Euler-Lagrange equations, which are d by dt of dou f by dou q dot k minus dou f by dou q k is equal to 0, where k is equal to 1 to n. And we define our f as L minus lambda g. And you see clearly here that unlike for the case of isoparametric problem where lambda was just a real number, now lambda has also become a function of t. Now you would ask why. The thing is, in holonomic constraints and also in non-holonomic constraints, we have to ensure that we meet this criteria. We meet this criteria at every point of the domain. So we have to satisfy this condition at every point where, so this is for all t is an element of t0 to, so lying in the interval t0 to t1. So which means that we have to have a, which means that we have to ensure this constraint at every point, and this makes that the parameter or the Lagrange multiplier which satisfy, I mean, so as to uh, for this constraint to be satisfied, we need a lambda at every point. So this makes lambda as a continuous multiplier, or as a continuous function, and that's why lambda is also a function, unlike the previous case. Now for non-holonomic or differential constraints, we have a functional of the similar form, which is j is equal to t0 to t1 of L t q vector comma q dot vector, where again q vector happens to be column vector of n dependent variables, and this is subject to two end conditions which are fixed in nature, and we have a constraint of which defined as g as a function of t q vector and q dot vector, and this equates to 0. So the thing to notice here is that the constraint in this case also contains the derivative of the independent or derivative of the dependent variable q vector. So for the necessary condition for extremization of such problems is given by the Euler-Lagrange equations, of where it's defined as d by dt of parcel k with of dou k by dou qk dot minus dou k by dou qk is equal to 0. And this holds for k is equal to 1 to n. And k is defined as lambda naught L minus lambda 1 as a function of t and into g. So for normal cases, we have lambda naught is equal to 1. And lambda naught, mind you, is a scalar here. And lambda 1 is a function of t. For abnormal cases, lambda naught is equal to 0. So this was our third constraint. Okay, now let's discuss about, so far we have been studying various new problems whose for which the values of the dependent variable was fixed at the ends. So in this case, so far we have been discussing about problems like such that say for this particular, so if you have this function here, so far y at x naught was some fixed quantity was fixed, and y at x is equal to x was also fixed. This was the case so far. But now what you would like to do is, and in many problems we see that the values at the ends are not always fixed. So let's introduce the conditions which are needed to be satisfied for those, for minimizing those problems or minimizing the functionals for those problems. So we start with functional j. It's defined as x naught to x1 f of x y y prime dx. It's just like any generic simple variational problem, and it's subjected to y of y at x naught is equal to y naught and y at x1 is equal to y1. In this case, the ends of the domain, which are x naught and x1, are fixed, while either y naught or y1 or both are variables. So this is what differentiates our current problem with the problems that we have been discussing so far. Okay, the necessary conditions for extremization of such problems is given by the Euler-Lagrange equation, which is d by dx of dou f by dou y prime minus dou f by dou y is equal to 0. And the boundary conditions are is given by eta into dou f by dou y prime from x naught to at x naught to and x1. So these are the endpoints for which this particular quantity has to equate to 0. Now you ask, okay, fine, but what if say, so there may be, let me discuss about three cases. So the first case is, say what if y naught is fixed. So y naught is fixed implies that eta at x naught is 0, isn't it? So what we are left with is, and y naught is fixed and y1 is say variable, then this implies that eta at x1 is not equal to 0. So this implies that the boundary condition will exist at, there will be one boundary condition at x1, and it has to be given by del f by del y prime at x1 is equal to 0. And you will ask, what if say y naught is variable and x1 is fixed? So y naught, or say y1 is fixed and y1 is y naught is variable, then this implies that dou f by dou y prime at x naught has to be equal to 0. And the third case is, what if both y1 y naught and y1 are variable? Then then we'll have the end conditions which has to be del dou f by dou y prime at x1 or x naught is equal to dou f by dou y prime at x1. Both have to be equal to 0. Okay, now let's see problems with variable boundary points, but the functionals which contain higher derivatives. So let me present the case for when we have terms up to second order derivatives in our functional. In this case, the necessary conditions for extremization is Euler Poisson equation, which is given by this second derivative with respect to x of the partial derivative of f with respect to the y double prime minus first derivative with respect to x of the partial derivative of f with respect to y prime plus dou f by dou y is equal to 0. And the boundary conditions are eta into d by dx of dou f by dou y double prime minus df by dy prime, dou f by dou y prime at x naught and x1 both have to be equal to 0. And eta prime dou f by dou y double prime at both the ends also has to be equal to 0. So with this we have covered the review of what the theory that was discussed in week 5 of this course. Let me just revisit what we have discussed so far. So we started with the constant extremation. We discussed just in a few sentences the need for having constraints and why does it occur in the first place, and the different types of constraints that we encounter in variational calculus. And there are of three types: integral constraints, algebraic constraints, and differential constraints. Then we just review the general formulation for isometric problems and the necessary conditions for the extremal, followed by that of holonomic or algebraic constraints, followed by non-holonomic or differential constraints. Then we just discuss problems. I mean the theory for variable boundary points where the domain remains fixed, but the values of the dependent variable at the ends may or may not be fixed. And then we discuss about the necessary conditions for extremation, and those with and also those the functionals containing higher derivatives of the dependent variables. So this was the overview of the theory required to solve the problems. Let me start with let me show you how to solve problems for all these different types of scenarios. So for the first part, we'll start with solving a problem, one or two problems on isometric constraints or isoperimetric constraints. So here we said that the question says that we have that find the extremals of the functional j of y is equal to 0 to 1 of y prime squared plus x squared dx, subject to the conditions y at 0 is equal to 0 and y at 1 is equal to 0, and the isoperimetric constant, which is y squared over the integral of y squared over 0 to 1 is equal to 2. Okay, so let me first write the auxiliary problem or the auxiliary functional. Let me write the auxiliary functional. Okay, so we start with f of x comma y, and this is defined as j of, or rather it should be just call it as f of just y is equal to j of y minus lambda of iy minus 2. So this lambda here enforces our condition, our constraint here. And this is defined as, let me write it here. So it's 0 to 1 y prime squared plus x squared plus x squared, and then minus, let me just call it minus lambda squared dx plus 2 into lambda. So this 2 lambda is a constraint here. I mean, it's a constant here. It's just a constant. So our this is going to be the integrand of the auxiliary function f. And since this is since 2 lambda is a constant, we can just ignore this particular term during our extremization process. So this we can just let's call it f. Okay, and this happens to be a function of x given y and y prime comma lambda as well. But for now, let's just give it short. In short, let's study it at f. The Euler-Lagrange equation is given by d by dx of dou f by dou y prime minus dou f by dou y is equal to 0. This implies that d by dx of dou f by dou prime is nothing but 2y prime, and so all the other, so we'll just have this term here minus dou f by dou y is nothing but minus of 2 into lambda y. This evaluates to 0, and we can factor out 2 throughout, and this gives us the differential equation y double prime plus lambda y is equal to 0. Okay, and as I had mentioned before, that lambda is a scalar and a real number, so to speak. So let's and lambda can be positive, negative, or even 0. So let's evaluate our choice for 3 different cases. So let me start with lambda is equal to 0. So this is the first case we're going to evaluate. For lambda is equal to 0, our differential equation or our Euler-Lagrange equation will become y double prime is equal to 0. And this gives us y, integrating it first gives us y prime is equal to, say, some constant a, constant of integration, and upon integrating it once more, you will have y of x is equal to a in ax plus b. Okay, let's determine the let's determine the constants using our boundary conditions, which are y0 is equal to 0 and y10 is equal to 0. Y at x is equal to 1 is equal to 0. So let's start with the first condition. So it is y0 is equal to 0. So this gives us y0 is equal to, or rather b is equal to 0. Likewise, y of 1 is equal to 0. This gives us a is equal to 0. Or rather a plus b is equal to 0, and then from this two we determine that a is equal to b is equal to 0. So which means we have we have the solution as y is equal to just 0. Now when we take a look at our isoperimetric constraint, it says that y 0 to 1 of y squared dx has to be equal to 2. But But the thing is, with the current, with the value of y that we have here, the function, the expression of the function y, this will evaluate to, so it just becomes 0, which is not equal to 2. So that means our lambda is equal to 1 is rejected. So this possibility is rejected. Now let's take when the case for lambda is equal to, or lambda is less than 0. So if lambda is less than 0, that means we can define lambda is equal to minus some alpha squared, isn't it? So which means that lambda in this case will always remain a negative number. Fine. Now putting this in our Euler-Lagrange equation, we'll have y double prime minus alpha squared y is equal to 0. And the general solution to such problems, as we had discussed in our first tutorial session, is nothing but y of x is equal to a into e to the power alpha x plus b into e to the power minus alpha x. Okay. So with this, what we have is, let's put our first boundary condition, which is y0 is equal to 0. This implies that a plus b is equal to 0, and this implies that b is equal to minus of a. Putting the second boundary condition, we have y1 is equal to 0, is equal to 0, then this implies that uh, a into e to the power alpha and minus a into e to the power minus alpha is equal to 0, and this implies that a into e to the power alpha minus e to the power minus alpha is equal to 0. And you know that exponential to the power any number except for minus infinity is never 0. So this means that this term is not 0. So the only conclusion is a has to be equal to 0. And because of this, even b will be 0. So we are left with the same situation as in the previous case. So yx is again 0. And this violates our isoperimetric constraint, since integral of 0 to 1 y squared dx is 0, which is 1 to isn't equal to 2, and the possibility of lambda becoming, or the possibility of lambda being a negative number is doesn't exist. So let's try the last condition. I mean the last possibility, which is lambda is equal to greater than 0. And like the similar procedure as above, we can have lambda is equal to some omega square. Remember that omega square will always be a positive number, because the square of any quantity is always greater than 0. Square of a real number is always greater than 0. So with this case, we'll have y double prime is equal plus omega square y is equal to 0, and then we have y of x. The general solution will be uh, a cosine x cosine omega x plus b sine omega x, isn't it? And upon putting the boundary condition, we have y0 is equal to 0, and this implies that a is equal to 0, and upon putting the second condition, y1 is equal to 0, and this implies that b sine omega is equal to 0. Since b cannot be 0, because then it will result in the same trivial condition, trivial value for y of x. So we'll take the second possibility, which is sine omega is equal to 0, and this omega becomes nothing but n pi, where n is an element of integer. You can have either a set of say something like positive integers. Okay, and then using this criterion of isoperimetric constant, we have same 0 to 1 to 1 y squared dx is equal to 2, and this implies that b squared of 0 to 1 sine square n pi x of dx is equal to 2, and then this evaluates to b squared by 2 is equal to 2, and then this means that b is equal to plus minus 2. So therefore the expression will be y of x of the extremal will be y of x plus minus 2 sine n pi x, where n is a positive integer. Okay, let's solve the second problem here in this isoperimetric problem. So this is more of showing that problem in the sense that we need to derive some quantity eventually. So the problem asks us to extremize a functional I is equal to x1 to x2 f of x y prime plus f of w with respect to functions yx and values of the quantity w for which j is equal to uh, integral over x1 to x2 gx y prime dx plus g of w is equal to k. So this j here is the isoperimetric constraint with y prescribed at x1 and x2. F and g are given differential functions of w. So we have to show that the required extremum is achieved if dou f star by dou y minus d by dx of dou y star by dou y prime is equal to 0 and f star prime w is equal to 0, where f star is equal to f plus lambda g uh, and f and capital F star is equal to capital F plus lambda capital G. Okay. So let's start solving this problem. So in problems like this, we'll first introduce perturbations. Say we'll introduce perturbations to y and w. Let's start with y. So y of y hat is equal to, this is the perturb value of y plus eta 1 epsilon 1 eta 1 x, and we require a second perturbation function which is eta 2 of x. Now I'll ask, okay, fine, but we were supposed to introduce perturbations to just y and w, but why do we require two perturbation functions? The thing is, we perturb the main function which is I with this, using this perturbation functions eta 1. However, if we introduce a perturbation to the functional, at the same time, these perturbations may not in general satisfy the isoperimetric constraint. So we require another perturbation functions to contract that such that we also satisfy our isoperimetric constraint. And this is provided by the second perturbation functions, which is eta 2 here. And mind you that both eta 1 and eta 2 are at least or are first order derivative, are differentiable at the very least. And the second, and then introducing perturbation to y to w gives us y w hat x is equal to w of x plus eta 1 and another perturbation function which is w1, or I'll not call w1, let me just call it mu1 x plus, and likewise we'll have second perturbation function here as well, mu2 of x. Okay. Now let's construct our auxiliary polynomial. So our auxiliary polynomial is, or sorry, our auxiliary functional is, let's call it by some name, maybe let's call it by p. P is equal to I plus lambda into j minus k. Fine. So this is our auxiliary functional. So let's expand it and by putting all our expression here, and let's do it on the next slide. So let's substitute our perturbation function here, which is perturbed quantities, which are x, y star prime, and also w hat and w hat prime. So this gives us integral from x1 to x2 of the term f as a function of x, y prime, sorry, f, y vector, and I'll just expand it here. I'll just call it y plus epsilon 1, eta 1 plus epsilon 2, eta 2, and y prime plus epsilon 1, eta 1 prime plus epsilon 2, eta 2 prime, and this plus lambda of g as a function of x, y plus epsilon 1, eta 1 plus epsilon 2, eta 2, comma y prime plus epsilon 1, eta 1 plus epsilon 2, eta 2, isn't it? This integral over dx plus capital F of since it's w here, so let me call it as w plus epsilon 1 mu 1 plus epsilon 2 mu 2, likewise plus lambda g of w plus epsilon 1 mu 1 plus epsilon 2 mu 2 minus lambda of k. So again, in this case here also we have lambda k is a constant. So we want to record this term, or as we'll see later that it automatically cancels out. So now let's introduce this term called, we'll call it as p. I'll just collect this term as well. Copy and then paste. So this minus p of x, y prime, w prime gives us x1 to x2, and what we do is let's expand the f in terms of a first order perturbation, first order Taylor series. Let's expand up to Taylor. Let's express this function in terms of a Taylor series up to first order in epsilon 1 and epsilon 2. So let me start with dou f by dou y into epsilon 1 eta 1 plus dou f by dou y in terms of eta 2, epsilon 2, eta 2, and likewise for dou f by dou y prime into epsilon 1 eta 1 prime plus tau f by tau y prime into epsilon, and this, okay, and epsilon 2 eta 2 prime. And likewise we'll have for plus lambda, I'll just call it as lambda g by g epsilon 1, this as a function of, I mean this in first in terms of epsilon 1 eta 1 plus epsilon 2 eta 2 plus lambda dou g by dou epsilon 2 epsilon 1 so beta 2, it should be just y, and this should be y prime epsilon 1 star prime plus epsilon 2 eta 2 prime. And you'll ask that, okay, where is the term in fx y and fx y y prime and gx y and y prime? The thing is, and gx y prime, the thing is, this particular term contained those terms and it just got cancelled out, so we only have the first order derivatives. Okay, fine. So plus, and ideally it should also be, it's say order of epsilon square terms remains to complete this procedure, but we are not considering that, since our necessary condition is essentially to derive the first order derivatives or first variation derivatives. So likewise we expand even this term, so we'll have dou f by dou w into epsilon 1 mu 1 plus epsilon 2 mu 2 plus lambda dou g by dou w epsilon 1 mu 1 plus epsilon 2 mu 2. So minus lambda k plus lambda k, so it was like minus lambda k and minus of minus lambda k, right? So it comes from both these terms, p in terms of the perturbed quantities and ps in terms of the quantities y and y prime, w and w prime. So this actually cancels out. So that was what we had wanted, and this is also, there will be again order of epsilon square terms, right? So what we do is, let's determine the expression of this, isn't it? So essentially what we have is, we'll have our problems in terms of the variation in two quantities, isn't it? So essentially our problem has reduced to a extremization in or in terms of finite dimensional optimization problem. So what we start with first is, let's call this quantity as say, what we do is, let's call this quantity as something like just call it as delta p, if you call it like that. And what we do is, let's first find the derivative with respect to say let's take it to be df by epsilon 1, where such that we have epsilon 2 is equal to 0 and this limiting as epsilon 1 tends to 0. So this gives us x1 to x2. So this one will give us dou f by dou y, isn't it? And since epsilon 2 is 0, we'll have that we will not require the second term won't be there, into eta 1 plus, again likewise here it is prime into eta 1 prime. This term won't exist, which is dou f by dou y prime, and likewise here also we'll have lambda into dou g by dou y into eta 1 plus lambda dou g by dou y prime into eta 1 prime, and so this is with respect to dx. And since order epsilon square divided by epsilon 1 or epsilon terms, we'll just, as epsilon 1 goes to 0, this term will eventually this term becomes 0, so we'll have just this term. And likewise for the extra term, which is dou f by dou w into mu1 plus lambda into dw by w into mu1, isn't it? So this becomes, this we have to equate to 0, isn't it? So essentially what, and then what we'll do is this limiting term essentially is nothing but d dou p by dou epsilon 1. And what we need to do here is, let's first take terms which containing just eta here. So it is dou f by dou y plus lambda dou g by dou y into eta 1 dx. And let's apply our integration by parts to the terms containing derivatives in the perturbed functions. So we'll have the first will be dou f by dou y prime into eta 1 plus lambda dou g by dou y prime eta 1. This is at x1 and x2. These are essentially the boundary points. We have to evaluate this term at the boundary points, and then minus of x1 to x2 of nothing but d by dx of dou f by dou y prime plus d lambda into, lambda is a scalar, mind you, so dou g d by dx of dou g by dou y prime, and then into, we'll call it as eta 1 into dx, and we'll have more terms which are nothing but plus dou f by dou w mu1 plus dou f by dou w, sorry, lambda into dou g by dou w into mu1 has to be equal to 0. So I can just factor them out such that we'll have plus dou g by dou w into mu1 is equal to 0, isn't it? So essentially, let's rewrite it, the entire expression in a compact form. So we'll have dou p by dou epsilon at epsilon 2 is equal to 0, right? So this is the condition. So I said right here that actually we are finding at epsilon 2 is equal to 0, which is anyway, it's the same thing, even if you don't write this. And then we write in the expression in a compact form, which is, let me call it as dou by dou x of, not dou x, it is dou by dou y of f plus lambda g. Mind you that lambda is a scalar, so it's we don't need to worry about it. It's not a function of x or it's just a pure number. And then minus of d by dx of dou by dou y prime f plus lambda g into, and this will be in terms of eta 1, isn't it, into dx, and this term that we already have here, so it is dou f by w, and I'll also write it in a standard form, which is in a compact form. So this, and into mu1 is equal to 0. Now from the fundamental lemma of calculus of variations, we have for arbitrary variations, because lambda eta 1 and mu1 both are arbitrary perturbation functions, right? So for this to hold for all perturbation functions, all that we require is we must have, the first term is we must have this thing, we must have this condition, that the integrand has to be equal to 0. This is also our Euler-Lagrange equations. And the second condition is for, since it has to also hold for arbitrary variations mu1, so our second condition is that we'll need to have and this f, since f is a pure function in w, we can also write it as f plus lambda g prime with respect to w is equal to 0. So these are our conditions. Now if you repeat the process again, say if similarly we can obtain the same expressions even for at epsilon 1 is equal to 0, this would lead the same conditions as above. Okay, and so yeah, we were able to solve this particular, right? We are able to solve both these things, and we're in more compact form. We can just call, say, f star to be f plus lambda g, and then f star is equal to capital F plus lambda capital G. So then so we showed what was asked in the problem. Okay, now let's discuss problems on say holonomic constraints, and let's do this for a case of so the problem says that among all curves lying on the surface x squared plus y squared plus z squared is equal to a squared, and passing through two given points x0, y0, and z0, and x1, y1, z1, find the one which has the least length, isn't it? Now what we do is let's first formulate our problem. So we have to find the least length, right, on a of a curve joining 2 points on a sphere. So our goal is to essentially extremize a functional j of x, y, and z such that we'll have x0, y0, and z0 to x1, y1, z1, and we require to dx squared plus dy squared plus dz squared. So mind you that this gives us the length. an infinitesimal length between 2 points which are infinitesimally close to each other. But what we see here is we can what we can do is we can parameterize our x, y, and z in terms of some parameter t, and that helps us to express this functional in terms of a single independent variable, and which will help us in our computation or in our derivation process, in the process of derivation. So what we do is, let's take x as a function of t, y as a function of t, and z as a function of t, right? So what we have is d. So with this, and the condition is that at t is equal to t naught, you will have x, y, z is nothing but x naught, y naught, and z naught. Likewise, at t is equal to t1, you will have x, y, z is given by x1, y1, and z1, right? And what we can do is, so d of x is nothing but dx by dt into dt, right? And this is nothing but x dot dt. And similarly for say dy is equal to y dot dt, and dz is equal to dz dt, or z dot dt. Fine. So our functional here becomes j of x, y, t, and this is from t naught to t1, and then in a very nice fashion we are able to write it x naught square plus fine to dt, right? Okay, so this was our function, and we have also laid down our boundary points. So these are our BCs, or the boundary conditions, and our we have a holonomic constraint, right? And the holonomic constraint is uh, g of x, y, z, all as a function of t, is nothing but x square plus z square minus a square is equal to 0. Fine. Okay. Now what we do is, now let's construct an auxiliary functional. Isn't it? So the auxiliary functional will be say capital F is equal to j minus, well, I'll just write the entire expression, t1 to t2, and then root over plus y dot square plus square dt minus of t naught to, actually it was t naught to t1, t naught to t1 of lambda as a function of t into the rest, which is gxyz. So it is x square plus y square plus integrated. Fine. So this is our, and in a single we can write this as x dot square plus and then in terms of dt. Fine. Okay. So this, let's call it as our the integrand is f. Fine. So let's derive our Euler-Lagrange equations. What you see closely here is f happens. There are three dependent variables which are x, y, and z, and there is just one independent variable which is t. So when we so the first Euler-Lagrange equation will be say with respect to d by dt of dou f by dou x dot minus dou f by dou x is equal to 0, isn't it? And then this gives us x dot divided by root over plus y dot square plus minus of minus lambda into 2x, right? This is equal to 0, isn't it? So the equation is nothing but x dot by square plus y dot square plus z dot squared plus 2 lambda x is equal to 0. Fine. And likewise for repeating this process for dou y dot minus dou f by dou y. This gives us a similar expression, which is y dot. This should be, I think I had done some mistake here. This should be d by dt. So similarly, d by dt, and again d by dt of, and likewise dou z equal to 0, and this gives us d by dt of z dot minus root over x dot square plus. Okay. Now when we look clearly at this expression, what we see here is we have three. So we have three equations, and each of the equations are second order in the independent variable. And you'll ask how it's second order. The thing is, if you use partial, what do you call some sort of a chain rule to differentiate this quantity within the parenthesis, then you'll find that the first term we'll have is x double dot divided by root over x dot square plus y square plus z square, and likewise it will fill for all the three equations. So essentially, every term is two second order in t, isn't it? So essentially, so so essentially we have six. So all these three equations are second order in t, and you know that a second order equation has two linearly independent solutions. Fine. And what more do you see? What you see here is, so, and then they're also related. These x, y, z are related through I mean, by its virtue of lying on a sphere, isn't it? So which means in some way x, y, and z are also linearly dependent because they are constrained to lie on a surface. And what we can do here is let's try something out. Or what I'll do is um, um, instead of let's what we do is I'll just give some final results in this because this problem tends to be tedious and we have a lot of more problems to solve. So what's it said, what's is holds here is that given a sphere, right? So let's have a sphere here and joining any 2 points on a sphere, which and for the curve joining these 2 points to have, say this is T naught and this is T1 in the parametric space. So which is this x naught, y naught, z naught, and this is x1, y1, and z1. So these are the endpoints. So what you see is if you take a curve which connects these 2 points on a sphere, and what you'll see is it actually lies at the intersection of a plane contains which contains this contains the curve, and this plane actually passes through the origin. Now equation of a plane isn't it? The equation of a plane is given by the general equation is ax plus by, or in of a plane in 3D is given by ax plus by plus cz is equal to d, right? Here 3D is a three-dimensional space. I'll just call it 3D to avoid any confusion. Three-dimensional space. Now, since the plane which contains the curve also passes or has to pass through the origin, we will have, if you put x is equal to y is equal to z is equal to 0, so then we can determine the quantity z here. So this implies that, sorry, it's d here. So this implies that d is equal to 0. So therefore, the equation of this plane here is ax plus by plus cz is equal to 0. So the curve is actually lies in the plane, which is given by ax plus by plus this one. And so essentially, uh, so the geodesics or the line curve connecting these 2 points are some sort of a part of a great circle in the on this sphere. So this is the equation. So these are just the final points that I wanted to make in this for this problem. And due to lack of time, we are not fully solving it. However, let me tell you the steps. What we need to do is first, what we need to do is we need to eliminate lambdas. And how will you eliminate lambdas? So the first step is when you take a look at the curves, right? X square plus y square plus z square is a square. Right? Let me write it here. X square what we do is let's differentiate it with respect to x. So this gives with respect to t. So this gives us 2x x dot plus 2y dot plus 2z dot is equal to 0, isn't it? And then what we see here is we're essentially x double dot x dot plus y dot plus. So you can use this equation to eliminate lambdas from all these equations, right? So how will you do that? You will first multiply, or let me do it. Let me just do it, even if we have less time, but let's do it. So what we do is, uh, let me call, let me just give a short name. Let me call root over x dot square plus y dot square plus z square. Let's give it some function. Let's call it by um, take some function, say g, or I'll call it h of t is equal to 1 by root over, let's call h, just h, simply h is equal to 1 by root over x dot square plus y dot square plus z dot square. Fine. And what we do here is, let's multiply the first equation with x dot, second by y dot, and third by y dot, z dot, and add them up. So then this gives us uh, multiply, I'll just write as multiply first equation by x dot, second by y dot, and third by z dot, and add all of them, all. So then this gives us x dot of d by dt of h into x dot, right? Isn't it? H of x dot plus y dot of d by dt of h of y dot plus z dot of d by dt of h z dot is equal to 0. Not is equal to 0, plus 2 into lambda, and then lambda into x into x dot plus y dot plus z dot is equal to 0. Now you recognize something, right? This term evaluates to 0. So what we have essentially done, we have essentially eliminated lambdas from our equations. So we will have x dot, and then d by dt of h x double dot and then similarly is equal to 0, isn't it? Okay. So what we can do here is, uh, so mm, if we multiply, say, let's just try out something. Say if we multiply by h throughout, and we know very well that h cannot be 0, right? Because it x, y, and z can, and x dot y dot are they are this form something known as a regular curve for which derivative is never 0. I'll just call that h is not equal to 0, and then say if we multiply h throughout by h, say multiply, let's try something, I hope it works out, but h throughout. So then this gives us h x dot, and similarly y dot h y dot plus this one, right? So effectively, what does it give? Let me just call it h x dot into d by dt of h of x dot plus hy dot d by dt of hy dot plus hz dot d by dt of hz dot is equal to 0. Fine. And so this comes out to be, when we take its derivative, so I mean we can even write it as d by dt of hx dot squared, isn't it? Plus hy dot squared plus hz dot squared is equal to 0. Can we do this? Of course we can, right? And of course we can do this, isn't it? And this is throughout by 1 by 2. And this 1 by 2 we can take it to the other side and become 0. So then this gives us that we have hx dot squared plus h, or I'll just call it as h of h squared into x dot squared plus y dot squared plus z dot squared is equal to some constant c. And now let's put the expression for h squared. But what we see is, okay, I think we are proceeding in a very wrong direction. Okay, so it effectively says that it's equal to c, and this means c is equal to 1. Okay, I think there is some that it's not inconclusive. Okay, so I'll get back to you next time with this due to the lack of time. Now let's discuss a few problems on non-holonomic constraints. Okay, so the problem says that given a functional I is equal to from t0 to t1, sorry, t1 to t2, f of t y dot y double dot subject to the fixed end conditions. We are asked to pose this problem as one with non-holonomic constraint. Okay. So we are required to pose this problem as a non-holonomic, as a problem with non-holonomic constraint. Okay, so what we do is, let's make a substitution here. Take, and we'll see why we are doing it. Take z is equal to y dot. And this implies that y double dot is nothing but z dot, isn't it? So, so our functional here is I is y and z, and this becomes t1 to t2, and this is a t, y, z, and then z dot. So the function containing higher order derivatives of y has now reduced to a functional in two independent variables y and z, and now in terms of first order derivatives. And this is again subject to, we already know that we have fixed end conditions, so let's not write it. Let's just talk about the holonomic, and the non-holonomic constraint is nothing but g of y comma z comma is nothing but Let's call it as y dot z dot, right? Just for the sake, we'll have this is nothing but y dot minus z is equal to 0, isn't it? So we have a relation between y dot and z. So in this case, so essentially now our problem is one with non-holonomic constraints. And if we find the Euler-Lagrange equations, we will have, since the functional consists of two dependent variables, so let's find the first one. So d by dt of dou f by dou y dot minus dou f by dou y is equal to 0, and this gives us, and before that I'm jumping ahead of myself. So using this two, we can construct a function, say h is equal to f minus lambda as a function of t into g. So this means that this implies that we'll have h, and then this gives us d by dt of y dot. So this gives us um, let's just call it as dou f by dou y dot, and then plus, sorry, minus lambda, right? So this is f minus lambda of t into y dot minus z minus lambda, and minus dou f by, so it is nothing but dou f by dou y, and minus, or integrity is actually plus lambda into, so it's not lambda, it's just dou f by dou, sorry, it's just dou f by dou y is equal to 0. Fine. This was our first equation. And the second Euler Lagrange is d by dt of dou h by dou z dot minus dou h by dou z is equal to 0. This gives us d by dt of dou h by dou z dot is nothing but dou f by dou z dot. And one more thing that I must tell you is, in the functional here, f is no longer a function of y dot, right? I need to clarify this. If it's f of t comma y comma z dot, so it's no longer a function of y dot, sorry. So it's just this, I made a mistake here. Okay, it's nothing but lambda dot plus dou f by dou y is equal to 0. And in this case, this becomes dou f by dou z dot, and we don't have any, or there is a dot here, right? So it's this, and then minus dou h by dou z, right? So it is dou f by dou z minus it's a lambda t into, so dou f by dou z is plus 1, so it will be plus 1 plus lambda actually is equal to 0. And this gives us d by dt zt, isn't it, minus dou f by dou z and minus lambda is equal to 0. So we have two Lagrange equations. And if we want to eliminate, say lambda from the two equations, then we'll have is, we need to first differentiate the second equation, this with respect to t. So it is d square by dt square of dou f by dou z dot minus d by dt of dou f by dou z minus is equal to 0. And then this, mind you that lambda dot is nothing but is equal to minus of dou f by dou y, isn't it? And then so we have, and then we have d by dt squared, and then putting the value, I mean, z dot is nothing but y double dot minus dt by dt of dou f by dou y dot plus dou f by dou y. And this is nothing but Euler-Poisson equation for the actual function. So just to make an equivalence now between when we are using a non-holonomic constant uh, and how it will directly be. So it essentially non-holonomic constant can be used to convert a problem or a functional containing higher derivatives in dependent variables to one with first order derivatives, and we create extra independent variables. So that's essentially and this can be used or are widely used in different areas of engineering. So now let me start discuss about say variable problems with variable boundary points. Okay, so the first problem here says that minimize the functional I with left endpoint fixed and y at y of x1 is along the curve x1 is equal to pi by 4. Okay, let me just make a diagram here for the schematic of the problem. So we have this rectangular axis or Cartesian coordinate system here, and say at x is equal to 0. So this is the x is equal to 0 line. These are origin x, y. It says that our left end point is fixed. So okay, so on this side we have say y1. This is y0, fine, 0 comma y0, and the second it says that it can lie anywhere this curve. So let me call it here. So this is y at x1, and x1 here is given by pi by 4. So this x1 is called pi by 4 line. So we need to find a function, anything of this, which is connected on the left hand side to a fixed point 0 comma y dot, and on the right to a point lying on this line, which is x1 is equal to pi by 4. So essentially, what we see here is there is a problem with a variable boundary point at the right end. Okay, so for if I so we have a function is given here, and the BC is here is we are just given one point, which is y of x naught is equal to, or y of 0 is equal to y naught, which is fixed, and about the y at x1 is unknown, right? Now if you go back to our section on the theory for variable boundary points, so the BCs, first we need to find the usual Euler-Lagrange equation, and then the BCs here is eta into dou f by dou y prime, and x naught and x1 is equal to 0. So in our problem, we have y naught is fixed and y1 is variable. So which means that we need to satisfy, we'll have our, the boundary condition here is dou f by dou y prime at x1 is equal to 0. Fine. Okay. So let's go back to our problem and let's list on this point. So EL equation is nothing but um, d by dx of dou f, and f is not f is here is this is our f, and equal here is I is equal to 0 to x1 f of xy y prime to dx, isn't it? So our so this is our boundary point here, and then f of x, f is nothing but y squared minus y prime whole squared. Fine. This minus dou f by dou y is equal to 0. And then this implies that d by dt of minus 2y prime minus of 2y is equal to 0. And then this factoring out minus 2 gives us y double prime plus y is equal to 0. So these are Euler-Lagrange equation. And this is nothing but the general solution is ax, y of x is equal to a cosine x plus b sine x. And now let's look at the BC at, look at the basis first, basis. And then those bases will be used to evaluate the constants A and B. So y of 0 is equal to y naught. So using this, we have a is equal to y naught, right? Because cosine of x at 0 is 1 and sine of x at 0 is 0. And the second condition what we had seen is y by dou y prime at x1 is equal to 0. So this evaluates to dou f by dou y prime is nothing but minus y naught sine x plus b cosine x at pi by 4. x1 x is equal to pi by 4 is equal to 0. So this gives us minus y naught by root 2 plus b by root 2 is equal to 0. So this gives us b is equal to y naught, right? So therefore the solution is yx is equal to y naught into uh, cosine x plus sine x. So this is our solution to the problem with fine. And say if y naught is 0, so if one end of the curve is located at the horizon, then obviously y naught is on, so y naught will be 0. So this implies that or we'll get a trivial solution, which is y of x is equal to 0. Okay, now let's move on to solving the second problem. So the second problem asks us to find the extremal of the functional I where endpoints of y are free. But the domains, what we see is that the domain is fixed. So let me draw a schematic of the problem. So the schematic is draw the Cartesian coordinate system. Okay. This is at x is equal to 0 line. And this is at x is equal to 1 line. Fine. So we can have any curve which lies at whose endpoints lie on these two lines, isn't it? So which means that the let me call this as 0 comma y naught, and this is 1 comma y1. So the end values of y are both unknowns. So here y naught and y1 are both unknowns. Okay, so let's first find the Euler-Lagrange equation of this problem. So the EL equation here is, and we'll have say f is equal to y prime squared by 2 plus y dot plus prime plus y. So the EL equation is d by dx of dou f by dou y prime minus dou f by dou y is equal to 0. So then this implies that d by dx of dou f by dou prime is y prime plus y, isn't it? Plus y and plus 1 as well, and plus 0 here. Minus dou f by dou y is y prime plus 1 is equal to 0. Okay, so then this gives us what what does this give us? This gives us y double prime plus y prime plus 1 minus plus 0 minus y prime minus 1 is equal to 0. This cancels out, so the Euler Lagrange is y double prime minus 1 is equal to 0. Or likewise, we can just call it as y double prime is equal to 1. Okay, so let's integrate twice with respect to x to get so the first integration, say dy by dx, this gives nothing but x plus some constant capital A. Integrating it twice, again once more, gives us y of x is nothing but x squared by 2 plus ax plus b. Fine. So we are required to determine the constants a and b, isn't it? From the previous question, what we saw is when one and when our uh, well, this is the one. Is it or where did it go? Let's copy this. Okay. Mm, okay, and we'll see it later. There is an issue because one of the okay, fine, anyway. So okay, so it is okay. Okay, fine. So all that we had to do is then our after integrating it again, we have x squared plus 2 plus ax plus b, right? And from the previous problem, what we have seen is with when let's apply the bases now. But for us, our bases will be del f by del y prime at x naught, or in this case at x is equal to 0, has to be 0, and del f by, and we'll have at del f by del y prime at x is equal to 1 is also 0. Okay, so let's start with the first one. Okay, so let's start with the first one. So this is our boundary condition, so to speak. So del of by del y prime at x is equal to 0 is it's nothing but y prime plus y plus 1 at x is equal to 0 is 0. So then this gives us y prime is nothing but x plus a, right? And so x plus a plus, and y is nothing but x squared by 2 a into x plus b plus 1 at x is equal to 0 is 0. So this gives us a plus b plus 1 is equal to 0. And likewise, we have the second condition as y prime plus y plus 1 0. So then this gives us, we'll have the x plus a plus x square plus 2 plus ax plus b plus 1 at x is equal to 1 is 0. 1 plus a plus 1 by 2 plus a plus 0, right? And what we see from the previous equation, which is, let's just call it equation 1, and this is equation 2. So from 1, we have a plus b plus what you call, or I'll rather call it substitute 1 into. So in this case, we'll have a plus b1 is equal to 0. And then this gives us a plus 3 by 2 is equal to 0. And then this gives us a is equal to minus 3 by 2. And for the second problem, I mean, for the second constant of integration, all we need to do is we'll use a plus b plus 1 is equal to 0. And since a is minus 3 by 2 plus b plus 1 is equal to 0. So b is nothing but, therefore b is equal to 1 by 2, right? So essentially our extremal for that functional is y of x is equal to x squared by 2 and minus 3 by 2 and plus half, right? So this essentially solves the problem. Now let's solve a problem, last problem in the series. So the problem asks us to find the curve joining the points 0, 0 and 1, 0 for which the integral 0 to 1 y double prime is a minimum if y prime of 0 is equal to a and y prime at 1 is equal to b. Fine. So solution. So let's formulate this problem first. So our minimization is, our function is y of prime is equal to 0 to 1 y double prime square dx, right? And subject to basis y of 0 is equal to 0 and y of 1, no, y of 1 is also equal to 0. Let's derive the Euler-Lagrange equations. So in this case, since it's double derivative in y, so we'll have Euler-Poisson equation, and which is given by d of d square and this let's call it as f. So it is del f by del y double prime minus d by dx of del y by del y prime plus del f by del dou f by dou y is equal to 0. So this term is 0, this term is also 0. So all we are left with is d squared by dx squared of this is nothing but 2y double prime to 0. So we are left with fourth derivative or fourth derivative of y with respect to x is equal to 0. Fine. Let's integrate it sequentially. Integrating. So d cubed y of dx squared is equal to some constant. We'll call it by a. Let's call it a. And then second integration gives us ax plus b. Third integration gives us ax squared by 2 plus bx plus c. And fourth integration gives us ax cubed by 6 yeah. So what we see is we have for the first part of the problem we have y prime at 0 is equal to a, y prime at 1 is equal to b, and from the very definition of the problem we have y of 0 is equal to 0 and y of 1 is equal to 0. So which means we have four boundary conditions and we have four constants. So I will just tell that apply BCs to get y of x. I'll just write the final expression. So this is nothing but a plus b x cube minus 2a plus b to x square plus a x plus d is 0. So here is the solution. Now we can just verify it. Say let me put y of 0 is equal to 0. So yeah, that's true. Y of 1 is equal to 0. 1 I put here, 1 here, 1 here. So it is a plus b minus 2a minus b plus a. So minus b plus b cancels out, and then a plus a 2a minus a. So perfectly, yeah, this is our solution. You can verify both the other boundary conditions. Now for the second part, it says that the second part says that once you that our no other conditions are specified, so it simply means that y prime at 0 and y prime at 1 are unknowns. Okay, or yeah, they are unknowns or variables. So let's go back to the problem when we let's go back to the theory which describes about when we have higher order derivatives for variable boundary points. So our conditions are these are the two conditions. So eta, let me write. But for what we see is eta here are the perturbation functions. But at x1, x0 and x1, our dependent variable, which is y, they are already fixed. So which means the first condition is already satisfied. So we don't require this set of boundary conditions, this one. We'll only take this condition here. We'll only pick eta double prime. Okay, eta double prime dou f by dou double y is at x1 and x2 is 0. So we have eta prime dou f by dou double y double prime at x is equal to 0 is equal to 0 and eta prime at del f by del y double prime at x is equal to 1 is also 0. Now what we see here is eta prime is nothing but perturbation to y prime at x y prime. Yeah. So eta prime is perturbation to y prime. So since y prime at x is equal to 0 and x is equal to 1 are unknowns, so this simply implies that eta prime at 0 isn't equal to 0 and eta prime at 1 isn't equal to 0. So what we are left with is, this implies that del f by del y prime at x is equal to 0 is 0, and eta f by del f by del y del prime at x is equal to 1 is also 0. So from the first condition we have is del f by del y double prime is nothing but we'll have 2 del y double prime, right? So this gives us 2 del y double prime at x is equal to 0 is 0, and we can just factor out 2, so it is y double prime at x is equal to 0 is 0. And from our expression, from the general expression here is y double prime is nothing but ax plus b, right? So ax plus b at x is equal to 0 is 0. And then this gives this as b is equal to 0. From the second condition we have again del f by del y double prime, and this gives us ax plus b at x is equal to 1 is also 0. So what we see is b is already 0, so then this implies that a is also 0. So therefore our so therefore our y of x, for now it will be just cx plus d, right? However, to determine cx plus d, we require y of 0 is equal to 0. So then this implies that d is equal to 0, right? And y of 1 is equal to 0. This implies that c is also 0. So that effectively y of x is equal to 0 throughout. So this is our solution. So with this, yeah, we end our tutorial session. And if you have any problem, please let me know before I conclude today's discussion. So please let me know if you do you have any doubts or. Okay, so it seems that there are no doubts. So what I'll do is let me conclude today's session here. And please let me know any doubts in the next tutorial session. So okay. So happy solving assignment for week 5. So thanks. Let's meet in the next tutorial session on 7th of March. Okay, bye.